All right, we're on page 28 today in your packet. These are notes on speed and velocity. It's going to be pretty quick, and the notes today are fairly easy as well. Shouldn't have any problem understanding the concepts we're going to talk about today, because most of you already understand speed and velocity for the most part. There's just a few things that we need to get down. First thing I do need to tell you is that the notes, this is my fault, but the notes don't go along very well with the PowerPoint. So I'm going to tell you periodically about some things that are not in the PowerPoint. So the first thing I'm actually going to talk about is not in the PowerPoint. So I want you to go all the way down to the bottom of page 28, all right? And down there about the bottom inch or two, I want you to write these two terms, scalar and vector, right? Write the word scalar on the top, vector on the bottom. You're going to define those two. The definition of a scalar, these are two types of quantities that we're going to talk about this year in physics. A scalar has only magnitude or size, and you might want to put out beside that the word number, right? Scalar is just the number, or the number of the measurement of something that we take or that we calculate in this class, as opposed to a vector, which has both magnitude and direction. And that should ring a bell to you because we talked about distance and displacement last time in class, and you should remember that the only difference between those two was that displacement has a direction associated with it. So without using these words, we've actually already talked about scalars and vectors. All right, so here's some examples of some scalar quantities. Distance is one of them. When you talk about a distance, you're not concerned about the direction, you're just concerned about the number, the magnitude, the size. Speed is another one. Mass, time, density, work, energy. Also weight. When you report your weight, you don't say 150 pounds down. You don't give a direction with it. It's just a number. As opposed to these, which are vectors. Displacement is the vector counterpart of distance. Velocity is the vector counterpart of speed. Acceleration, force, momentum, these are all vectors. They have magnitude as well as direction. Okay, so we have scalar quantities, we have vector quantities. All right, so that's scalars and vectors. Let's go back up to the top of the notes, look at the words speed and velocity. All right, so speed, tough definition, right? Tough to understand. Speed, here it comes, is how fast something is moving. I know, crazy, right? It's kind of hard to wrap your mind around that one, how fast something is moving. But try as hard as you can and see if you can understand that. No, you guys understand this point. This is the reason why we start with motion. It's easy to understand. We get it. Speed is how fast something is moving, right? But why is it always a positive number? That's a question that I need you to think about. So at first that may not make sense to you, because you might remember last time I told you that we can go negative 30 miles an hour in our car. Because remember, a negative and a positive in this class only indicates direction, right? So why are we now saying that speed can only be positive? Well, the answer is that speed is an example of, remember just a second ago we talked about scalars and vectors. Speed is a scalar, right? And for that reason, speed does not have a direction. So when we talk about speed, we're not concerned about direction. So it has to be positive. We don't put a positive or negative on it. When the cop comes up to tell you your speed when you get pulled over, he doesn't also tell your direction, because nobody cares about direction at that point. It's just a number. It's just a magnitude. All right, the next two terms are actually not in your notes, average speed and instantaneous speed. It's a pretty simple concept, but I want you to find a place somewhere in your notes and briefly write down the definition of these two things. You don't have to write it down verbatim, but average speed and instantaneous speed. Here's the concept, the difference. If I was to ask you how fast you went when you came to school this morning. I did this in my classes yesterday, and someone said 35 miles an hour. All right. So the question is, well, did you go 35 miles an hour the whole time? Well, no, of course you didn't. We understand that. We understand that that's even a hard question to answer, because you don't go 35 miles an hour the whole time. If you do, you're not going to arrive alive, or you're going to get a ticket on the way there. But we understand there are some stops in between. There are some times when you speed up. There are some times when you slow down. You go many different speeds during the process. And so the concept of average speed takes all that into account. So we talked about before, the concept of speed is distance divided by time, an equation which we'll introduce in just a minute. And then let's just say you live 5 miles from the school, right? That's the total distance you traveled this morning to get to school. And let's say it took you 10 minutes to do that, right? You didn't go 35 miles an hour the whole time, but I can calculate your average speed by simply doing the total distance divided by the total time it took you to get here, which is about 1/2 a mile per minute. And we can convert that to miles per hour or meters per second, whatever it is, but 1/2 a mile per minute is your speed, your average speed on that trip. It doesn't mean you're going 1/2 a mile per minute the whole time. It just means that on average you were moving 1/2 a mile per minute. That was your average speed. As opposed to the concept of instantaneous speed, which is a little bit easier, it's simply the speed at any particular instant in time. So this morning you did have an instantaneous speed of 35 miles an hour or 20 miles an hour or 0 miles an hour, whatever it is. That was your instantaneous speed. You need to put this equation down somewhere and make sure you have all the defining the variables. So V equals d over t is our first equation of the year. It's number 1 in your equation chart. Very important equation. We're going to use it quite a bit. So you need to know we use V, the letter V for speed, D is distance, T is time, and these are probably the most important part of the deal. The units that you need. Remember a while ago I told you that in this class every equation we have has specific units associated with it, and for this one happens to be meters per second for speed, meters for distance, and seconds for time. So make sure you write that down. Make sure you understand that to calculate speed for this equation you have to have speed in meters per second. What that means is, as you read your problems, you're going to have to really check and make sure that everything is in the units you want. For instance, if you have a problem that says John went to school this morning and traveled at a speed of 35 miles per hour, when you see that miles per hour, there should be a red flag going off in your head, and you need to say, okay, miles per hour, I don't like that anymore. Anything conventional I don't like. I've got to convert miles per hour to meters per second. And that's the reason why for the last few weeks we've been doing so much unit conversion. It's very, very important you know how to do that, because you will be asked to convert from time to time. All right, and then velocity is a simple addition. It's simply speed, and then we add direction to it. And remember from last time, direction is expressed as positive or negative. You don't have to write down what positive and negative means, because if you look across the page on page 27, you should have already written that down, so we don't need to worry about that. Average velocity and instantaneous velocity, those are the same concepts as average speed and instantaneous speed. It's just that now we add in the concept of direction with it. And this is the same equation as well. So not really much of a difference here. Okay, so remember, again, this is review. Distance and displacement are not quite the same thing. Displacement, remember, is the change in position from the beginning to the end of a trip. We talked about that definition of displacement last time. And we talked about this example too, about running around the track and finishing in the same place. You ran a distance of 400 meters, but your displacement is 0 because you started and ended in the same place. Okay, so that's the difference with those two. Now with this equation, V equals d over t, it's important that you understand that you will not only have to solve for V, but also distance or time. You'll need to algebraically manipulate this equation to find any and all of these. So it's important you know how to do that. If you're not good at algebra and you don't know how to manipulate that equation, this is going to be a good thing for you. So I would find a place to write this down, write this triangle. You can use this triangle with any equation that has this form, V equals d over t. And you can simply transfer this equation onto the triangle. You put whatever's on the left-hand side of the equation on the bottom left, and the other two go over each other just like they're over each other here. Okay, and the way we use the triangle is you simply put your finger on the one that you want to solve for, and the other two will tell you what to do, algebraically speaking. So for instance, the equation itself says if we want to solve for V, we have to do d over t, or d divided by t. That's what this equation says. But let's say we want to solve for d. If we want to do that, what we have to do is the other two, V times t. So since they're next to each other, we multiply. And then say we want to solve for t, what we've got to do then is the other two, d divided by v, since they're over each other. Okay, so that's just the algebraic manipulations of this. The triangle does the same thing for you. All right. So now we've got this sample problem. I want you to talk to the person sitting next to you. Sub, if you would please pause the video in just a moment and allow the students to just work on this. I want you guys to work on it with the person next to you and see what you can come up with. And then in just a minute we'll play the video and see what you got. Pause now. Alright, so hopefully the first thing you notice when you read this problem is that when you read up to here it says 60 kilometers per hour. I hope you're automatically thinking, oh, I need to convert that because it's a speed, but I've got to have speeds in meters per second, not kilometers per hour, right? So let's convert that real quick in case you've forgotten how. So I've got 60 kilometers per hour, and the units we need to go to are meters per second. So that means we're going to take kilometers and go to meters. Hours has to go to seconds. All right. Remember, we do one of those at a time. Kilometers first. To get rid of kilometers, I put it on the bottom. Cancels out. I don't care what the number is going to be, but I know the unit has to cancel if it's on the top and bottom. And I'm going to put meters on the top because that's what I eventually want. And I do know the conversion factor between meters and kilometers. It's 1,000 meters to 1 kilometer. Remember, the number goes with the smaller unit. All right. So I'm looking here. Meters and meters, they match. Circle it because I'm done with that top unit. But I'm not done completely. I got to get rid of hours and go to seconds. To get rid of hours, since it's already on the bottom, I've got to put it on the top. Cancel it out, cancel it out. Seconds is what I want eventually. So seconds has got to go on the bottom, and there are 3,600 seconds in 1 hour. That's what I want. So I want meters over seconds, and now I have meters over seconds. All my other units are canceled out. So I will do 60 times 1,000 divided by 3,600, and you don't necessarily have to do it in that order. If you do that, you will end up with 16.67 meters per second, right? So that is now your speed, right? You can't use this one anymore. You can't use 60. So that's now our speed. And then as for the other things they gave us, hopefully you came up with the time they give you is 0.75 seconds. And they want to know how far you will travel during that time. How far you're going to travel is distance. All right, so obviously this is our equation. It's important to write the equation down before substituting in. I know this is a very simple one, but later on you will have very complex equations that it's important to write down the equation just in letter form before substituting numbers to make sure we get everything in the right place. All right, so now I'm going to substitute in. My V goes in here, 16.67. D is what I want. Time is 0.75 seconds. Using algebra, we would multiply by 0.75 on both sides. Or if you want to use your handy dandy triangle, we want D. That means we have to do V times T, which is exactly what we're doing right here. The velocity times the time. 0.75 cancels out. 16.67 times 0.75 gives us a distance of 12.5, and don't forget the units, meters. Always have to have units in this class. In math class we just dealt with numbers. In this class it's real stuff. We have to put units on it. Alright, so that's the end of the notes on this page.